The Sun, a blazing ball of plasma, the heart of our solar system. It's easy to forget in our daily lives just how crucial this star is. Without it, life on Earth wouldn't exist. Our planet would be a frozen, lifeless rock, adrift in the vast emptiness of space. The Sun's energy, born from nuclear fusion deep within its core, bathes our planet in light and warmth. It drives our weather, fuels photosynthesis, and quite literally makes life possible. But even stars don't last forever. Like everything in the cosmos, the Sun has a life cycle. It was born. It exists in a state of stellar equilibrium now, and it will eventually die. Understanding this cycle and how the Sun will eventually meet its end is a journey into the very heart of astrophysics. It's a journey that reveals not just the fate of our own star, but also the destiny of countless stars scattered across the universe. The Sun, like all stars, began its life as a cloud of gas and dust. This cloud, a nebula, collapsed in on itself under the relentless pull of gravity. As it contracted, the material at its center began to heat up, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. This fusion, the process of hydrogen atoms combining to form helium and releasing tremendous energy, marked the birth of our Sun. For roughly 4.6 billion years, our Sun has existed in this state, known as the main sequence. During this phase, a star's outward pressure, generated by nuclear fusion, balances against the inward pull of gravity. This delicate balance is what defines a star's life on the main sequence. But the hydrogen fuel that powers this stellar furnace isn't infinite. One day, billions of years in the future, our Sun will reach a critical turning point. It will have consumed the vast majority of the hydrogen in its core. This event will herald a dramatic new chapter in the Sun's life, one that will have profound implications for our entire solar system. Deep within the Sun's core, a nuclear furnace rages. Every second, millions of tons of hydrogen are converted into helium. This process releases the energy that sustains our star and allows it to resist the relentless crush of gravity. But this hydrogen, the lifeblood of the Sun, is finite. Over billions of years, the Sun has consumed a significant portion of the hydrogen in its core. As this core hydrogen fuel dwindles, the Sun's energy output will slowly begin to change. This change will be gradual at first, barely perceptible over human timescales. However, over astronomical periods, the consequences of this change will become increasingly profound. The delicate balance between outward pressure from nuclear fusion and inward gravitational pull will begin to shift, setting in motion a series of events that will ultimately lead to the Sun's demise. As the Sun exhausts its core hydrogen supply, it will enter a new phase of its life cycle. No longer able to sustain its current size, the Sun will begin to expand dramatically, transforming into what astronomers call a red giant. This expansion will be nothing short of breathtaking in its scale. The Sun's outer layers will swell outwards, engulfing the orbits of Mercury and Venus. Earth, our home planet, will find itself precariously close to this expanding inferno. The once familiar yellow glow of our Sun will give way to an ominous reddish hue. The temperature on Earth will soar, oceans will boil away, and the once vibrant planet will transform into a barren, scorched wasteland. This is the fate that awaits any planet unfortunate enough to orbit too close to a dying star. As the red giant Sun continues to expand, it will become increasingly unstable. Its outer layers, tenuously held by gravity, will begin to drift away into space. This shedding of material will create a breathtaking cosmic spectacle, a planetary nebula. These glowing clouds of gas and dust, illuminated by the dying star at their center, are among the most beautiful and awe-inspiring objects in the cosmos. They represent the final poignant act of a star's life, a final burst of glory before fading into oblivion. The Sun's planetary nebula will be visible for thousands of years, a ghostly reminder of the star that once warmed our world. But within this nebula, a new object will be born from the ashes of the dying star. At the heart of the planetary nebula, hidden amongst the expanding shells of gas and dust, lies the remnant of our once mighty Sun, a white dwarf. This stellar ember, incredibly dense and incredibly hot, is the final stage of evolution for a star like our Sun. A white dwarf is the leftover core of the star, stripped of its outer layers and compressed to an incredibly small size. Although no longer fueled by nuclear fusion, the white dwarf will continue to radiate heat and light for billions of years, slowly cooling over eons. The white dwarf that remains of our sun will be a mere shadow of its former self, but its gravitational influence will continue to hold sway over the remnants of our solar system. With the sun's transformation into a white dwarf, the solar system will enter a new era, one governed by the fading embers of our once mighty star. The planets that survive the sun's red giant phase will continue to orbit the white dwarf, their paths altered by the shifting gravitational landscape. These surviving planets will exist in a much different solar system than the one we know today. The once bright sun will have dimmed to a faint point of light, casting long, cold shadows across the surfaces of these distant worlds. The delicate gravitational dance that governs the orbits of planets will continue, but the tempo will have slowed, the music changed. The inner planets, Mercury, Venus, and Earth, face a grim fate as the sun expands into a red giant. Engulfed by the sun's outer layers, these planets will likely be vaporized, their constituent atoms scattered into the vastness of space. The outer planets, Jupiter, Saturn, Uranus, and Neptune, stand a better chance of survival. Though their orbits may be significantly altered, these gas giants are likely to weather the sun's death throes. However, their systems of moons will be thrown into disarray, with some moons potentially ejected into interstellar space. The asteroid belt, that collection of rocky debris between Mars and Jupiter, will also be profoundly affected. The gravitational influence of the white dwarf's sun, coupled with the gravitational nudges from surviving planets, could send asteroids careening on new and unpredictable paths. Some may even find their way to the inner solar system, posing a potential threat to any surviving worlds. The death of a star is not an abrupt event. It is a drawn-out process that unfolds over billions of years. The sun's transition from a main sequence star to a white dwarf will be a slow, inexorable fading. Yet even in death, the sun will leave behind a legacy. The planetary nebula formed from the sun's outer layers will eventually disperse, seeding interstellar space with the building blocks of new stars and planets. The elements forged in the sun's core, carbon, oxygen, nitrogen, and others, will find their way into new solar systems, contributing to the cosmic cycle of stellar death and rebirth. In a very real sense, we are all made of star stuff. The atoms in our bodies were once part of a star that lived and died long ago. And when our sun eventually breathes its last breath, it too will contribute to this cosmic recycling program, ensuring that the universe continues to teem with stars and planets for billions of years to come. The process of stellar death and rebirth is not unique to our sun. Across the cosmos, countless stars are living out their lives, some just beginning their journey, others nearing their end. Every day stars are born, and every day stars die. Some stars, much more massive than our sun, will meet their end in cataclysmic explosions known as supernovae, briefly outshining entire galaxies. These stellar explosions scatter heavy elements into space, enriching the interstellar medium and contributing to the diversity of elements we observe in the universe. The death of stars, while seemingly destructive, is an essential part of the cosmic cycle. It is through the death of old stars that new stars are born, and the universe continues to evolve and change. As we contemplate the death of our own star, we are inevitably drawn to questions about life beyond Earth. If life can arise in our solar system, could it also emerge in other star systems, orbiting stars very different from our own? And what happens to life when its host star begins to die? These are questions that astronomers and astrobiologists are actively exploring. The search for life beyond Earth is one of the most profound scientific endeavors of our time, and understanding the life cycle of stars is essential to this search. As we continue to explore the cosmos, we are likely to find that life is incredibly resilient and adaptable, capable of existing in environments far more extreme than we can currently imagine. And while the death of a star may spell the end for life on its closest planets, it also creates opportunities for new life to emerge elsewhere, in the vast and ever-changing universe.